So now let's use this bulk perspective, the balance between the total energy and the entropy, to try to rederive in a slightly different way our equation of the week. So in order to do that, what I want to do is equate the following two quantities. The change in entropy of a system when it undergoes a phase transition from a liquid to a gas, for example, let's just focus on liquid to a gas, must be, when you multiply it by the temperature, it must be equal to the change in energy of the system when it transforms from a liquid to a gas. And so let's now calculate those two things. Let's do the energy first. So now if you think about a liquid, the molecules are all close to each other and are touching, whereas when you think about a gas, the molecules are far from each other and not touching. So the total energy in a liquid is the number of molecules times the number of bonds per molecule times the interaction energy per bond. So that's, let's call the number of molecules capital N. Let's call the number of bonds per molecule little z, and then we're going to multiply that by U interaction. So now, of course, the total energy in a gas, we're going to say, is essentially zero, because the molecules are whizzing around and they don't really touch each other at all. So the change in energy is actually is just given by the energy from the gas. And now I have to set that equal to the change in entropy. So for that, what I have to do is I have to take, so kBT times N, that's the number of molecules, times the logarithm of the number of configurations that are available to each molecule. And so let's think about how to measure the number of configurations. Actually, it's a bit difficult. So instead, let me just write out this formula a little bit, and then it will become simpler, perhaps. So what I really need to compute is the change of entropy between the gas and the liquid. So that's N Kb, the Boltzmann constant, times T, times the logarithm of the number of configurations in the gas minus the number of configurations in the liquid. And so if we now use this wonderful property of the logarithm, that if you take the logarithm of one number minus the logarithm of another number, it's just the logarithm of the ratio of the numbers, what it turns out is that the change in entropy is actually equal to the Boltzmann's constant times the logarithm of the ratio of the number of configurations in the gas divided by the number of configurations in the liquid. And we have to, of course, multiply that by the number of molecules, because each molecule has its own entropy. So that means I multiply by N. And then remember what I told you, you have to also multiply by the temperature. And so our equation is that N times Z times U interaction is equal to N times T times Boltzmann constant times the logarithm of the ratio of the number of configurations. So if we now just cancel out the N's, we now have this beautiful formula that starts to look a lot like our equation of the week. It says that U interaction is equal to kBT times the logarithm of the ratio of the number of configurations in the liquid to the gas divided by Z, the number of contacts per particle. And that thing there, that ratio, the logarithm divided by Z, that's what we were calling C from before. That's what we meant. So that's very interesting. And now the question is how to calculate it. And the only thing that's really difficult in this is to calculate the number of configurations. So how do we do that? So to compute the number of configurations might be hard, but to compute the ratio of the number of configurations is a little bit easier. And I just want you to think about, if you were a molecule, how much more free you would be if you were in a gas than if you were in a liquid. You see, if you're in a liquid, you're confined to where you are. If you're in a gas, you can fly everywhere. And so a good proxy for the ratio of the number of configurations is just the ratio of the volume that you find yourself in if you're in a liquid or in a gas. So it's really just the ratio of the volumes that a single molecule inhabits in a liquid and a gas, and that's really what we mean by the ratio of the number of configurations. It's just how much space you have to move around in. So what we need to do is to calculate the volume of a fixed number of atoms of the gas and divide it by the volume of a fixed number of atoms of the liquid. So just to make it simple for ourselves, let's consider a mole of each. It doesn't really matter, but let's just consider a mole. And a good reason for that is that at 1 atmosphere, you can just look it up, the volume of a mole of gas is 22.4 liters, which corresponds to 22,400 cubic centimeters. So that's the volume that a mole of gas will occupy at 1 atmosphere of pressure. So similarly, if we want to know the volume that 1 mole of a liquid will occupy at 1 atmosphere, what we first need to do is figure out the molar weight of the volume of liquid. For water, the molar weight is 18 grams per mole. That's the molar weight. And it turns out that the density of water is 1 gram per cubic centimeter. So that means that 1 mole of water is about 18 cubic centimeters when it's liquid. So if we want to compute our wonderful logarithm, this constant c in our formula, what we actually now need to do is we need to take the logarithm of the ratio of 22,400 divided by 18. And if you compute this logarithm, it turns out, and this is, by the way, the natural logarithm, it turns out that this number is about 7. So that means that our constant c is about 7 divided by z, which is the number of contacts per particle. And so the number of contacts per particle is something like 5, 6, 7, something like that number. It really depends. And so that's why our constant is some number which is about 1. We give the number 3/2, which is what you would find if you would do a slightly more proper accounting of the various factors. But this really shows you the essence of the physics behind this formula. And the one comment I would make about it, which hopefully is apparent from the way that we're talking about it, is that this constant really actually depends on the conditions that you're in. So you'll notice that when we computed the logarithm of the ratio of the number of configurations, we used the volume that a gas occupies at 1 atmosphere of pressure. If you change the pressure, then of course the volume of gas will change, and that will change the logarithm of this ratio, which will change the constant. The variation of this constant is actually important and comes up and will come up when we talk about solubility, how much sugar or salt can you dissolve in water, questions like this, which are also really quite important for cooking and adding flavor to food.